Reciprocating pump weighing 150 Newton is mounted at the middle of a steel plate of thickness 115 cm, width 50 cm and length 250 cm, clamped along two edges. During operation of the pump, the plate is subjected to a harmonic force F of T is equal to 50 cos 62.832 T newtons. Find the amplitude of vibration of the plate. So here the given diagram. So this is clamped between two plates, that is it is like a fixed beam. So and F is given by as a function of 50 cos 62.832 T. So here coming to the solution, first here we'll have to find out the stiffness of the beam. So generally the amplitude is given by F by K minus amplitude x is equal F by K minus M omega square. So first we'll have to find out the stiffness. So stiffness comes from the either K is equal to the ratio of load and deflection, and deflection for a fixed beam is equal to WL by 192 EI. From this equation, K is equal to 192 EI by L cube, where L is the length of the beam, that is 250 centimeter, and I is the area moment of inertia of the beam, that is equal to BD by 12, that is 50 into 1.5 cube by 12, which is equal to 14.0625 centimeter power of 4, and E is the Young's modulus, and is equal to Young's modulus is given by here E is equal to 200 gigapascal, that is 2 into 10 power of 5 megapascal. So all the values are there, just substitute all the values in the equation and we can get the stiffness, which gives a value of K and is equal to 345.6 into 10 cube Newton per meter. So we have all the remaining values, that is at x is equal to 0, that is F of 0 is equal to 50 Newton. Sorry, at the initial stage, that is T is equal to 0, F is equal to 50 Newton, and from this and weight of the pump is 150 Newton, that is 150 by 9.81 gives the mass of the reciprocating pump, that is 15.3 kgs, and K is equal to 345.6 into 10 cube Newton per meter. So now substitute all the values in amplitude of harmonic response, that is equal to 50 into 1000 by 345.6 into 10 cube minus 15.3 into where omega is the 62.832 square. From the equation, force is given by generally cos omega t, m cos omega t, mg cos omega t. So from this we can get omega. So from the equation, omega is equal to 62.832 radians per second, so which gives a value of 0.175 mm. So in the option, the right option is C is the right answer. Is used to measure the pressure in a tank. The fluid usually has a specific gravity of 0.85 and the manometer column height is 55 cm as in figure. If the local atmospheric pressure is 96 kilopascal absolute, determine the absolute pressure within the tank. Here take density of water as 1000 kg per meter cube, and this is the given diagram, that is we will have to find out the pressure at this point. So here are the options. So here we can write it as the pressure at this point as P atmospheric plus rho gh, where rho is the density of the fluid used and G is the acceleration due to gravity and h is the height of this fluid. So here it is equal to 96 plus 0.85 plus 1009.81 into 0.55 is the height. So the value comes for at 100.6 kilopascal absolute. So in the option, the right option is C. C is the right answer. In a gas turbine, gas enters with a velocity of 60 meter per second at the rate of 6 kg per second and an enthalpy of 1000 kilojoule per kg. The gas leaves the turbine with a velocity of 160 meter per second and an enthalpy of 500 kJ per kg. The loss of heat from the gases to the surroundings is 25 kJ per kg. Power output of the turbine is. Here it is like a open system, so that we can apply here steady flow energy equation. So steady flow energy equation is given by m dot, that is mass flow rate, into h1 plus v1 square by 2 plus gz1 plus heat transfer, either heat supplied to the system or heat rejected to the system, and here m dot into h2 plus v2 square by 2 plus gz2 plus the work done by the system. So this is the rate of work done, that is power output of the system. So from this equation we can find out dw by dt. So here h1 is given by h1, the suffix 1 refers to the inlet of the turbine and suffix 2 refers to the outlet of the turbine, and here h1 is nothing but enthalpy at the inlet of the turbine and v1 is velocity at the inlet of the turbine, and let us say here z1 is equal to z2, so that both get cancelled, and here mass flow rate is also constant, so that here it is equal to m dot into h1 minus h2 plus v1 square minus v2 square by 2. So just convert it into kilowatts, it is by 2000 plus dq by dt. So from this equation substitute all the values, so you can get here dw by dt is equal 2916 kilowatts. So in the option, the right option is A. A is the right answer. Evaluated for a wind farm is observed to have steady winds at a speed of 8.5 meter per second. Determine the wind energy per unit mass. Here the options are 36.1 joule per kg, 38.2 joule per kg, 40.4 joule per kg and 42.6 joule per kg. Here we'll have to find out the wind energy. Wind energy is nothing but the kinetic energy observed by the wind speed. So here the kinetic energy or wind energy is equal to half mv square, but we will have to find out the wind energy per unit mass, so that it is equal to half v square, and here velocity of the wind is 8.5 meter per second, that is 8.5 square by 2, which is equal to 36.1 joule per kg. So here it is the wind energy per unit mass, or it is equal to kinetic energy stored in the wind. So it is equal to 36.1, and in the option, the right option is A. A is the right answer. 10 cm diameter copper ball is to be heated from 100 degrees centigrade to an average temperature of 150 degrees centigrade in 30 minutes. Taking the average density and specific heat of copper in this temperature range to be 8950 kg per meter cube and 0.395 kilojoule per kg degree centigrade respectively. Determine the total amount of heat transfer to the copper ball. Here the options are 92.2 kilojoules, 92.4 kilojoules, 92.6 kilojoules and 92.8 kilojoules. Sorry, here the options are 277.6 kilojoule and 153.3, 92.6 and 69.4. So coming to the solution, here we will have to find out the heat transfer to the ball, so which is equal to mcp delta t, where m is the mass of the ball and cp the average coefficient, average specific heat, and delta t is the change in temperature. Here we will have to find out the first mass, and is equal to rho into volume of the ball, where rho is the 8950 kg per meter cube, and volume of the sphere is 4/3 pi r cubed, where radius of the sphere is equal to 0.05 meters and is equal to 4.69 kg. So now the heat transfer to the ball is equal to 4.69 into, and average specific heat is given by 0.395 into the change in temperature is 150 minus 100 and is equal to 92.6 kilojoules. So here the right answer is 92.6 kilojoules, and in the option, the correct option is C. C is the right answer.